Hello everyone, welcome to my channel. So today I have come up with the next part of the solid state. In the previous video we have discussed about the classification of solids. This video is about the properties of solids, the electrical properties and the magnetic properties. So let's proceed. So the electrical properties are based on the conductivity. Solids are classified as conductors, semiconductors and insulators. So here we can see a chart showing the type of the solids and the conductivity range in ohm inverse, meter inverse. Conductors have a conductivity range of 10 to the power 4 to 10 to the power 7 ohm inverse, meter inverse, and insulators have a conductivity range of 10 to the power minus 20 to 10 to the power minus 10. Semiconductors have a conductivity range of 10 to the power minus 6 to 10 to the power 4 ohm inverse, meter inverse. Here we can see the comparison of the valence band and the conduction band in case of insulators, conductors and semiconductors. Valence band is in the low energy state and conduction band is in the high energy state. So in case of insulators, there is a large energy gap between the valence and the conduction bands. And if the gap between the valence and the conduction band is large, electron can't jump and they behave as insulators. In case of the conductors, you can see that conduction band is very close to the valence band and hence the electrons can easily move. So in case of metals, this case is seen and hence they are good conductors. In the third case, we can see that there is a small energy gap between the valence and the conduction bands. These are semiconductors. So some electrons can jump to the conduction band and show some conduction. On heating, electrons can jump easily and these are intrinsic type of semiconductors. Conductivity of intrinsic semiconductors can be increased by adding certain impurities. This is known as doping. Again, the doping may be of two types, that is, electron-rich impurities when element of group 14, that is silicon or germanium, having 4 valence electrons are mixed with some quantity of group 15 element such as phosphorus or arsenic have 5 valence electrons. They form 4 covalent bonds and the 5th unbonded electron is responsible for increased conductivity. This is due to the negatively charged electron and hence are known as N-type of semiconductors. You can see a figure showing arsenic doped germanium. So these are examples of N-type of semiconductors, that is silicon and germanium. Group 14 is doped, is mixed with element such as phosphorus or arsenic that have 5 valence electrons. So this form the N-type of semiconductors. The second type is the P-type of semiconductors. Electron deficient impurities when element of group 14, that is silicon or germanium, having 4 valence electron are doped with elements of group 13, that is boron or aluminium, having 3 valence electrons. 3 covalent bonds are formed. The place where the 4th valence electron is missing is electron hole An electron from neighboring atom can fill electron hole, but it leaves hole at its original position. Electrons and hole seem to move in opposite direction and cause conductivity. These are the p-type of semiconductors. An example is indium-doped germanium, as you can see in the figure. The magnetic properties of solids are classified into 5 types: the diamagnetic material, paramagnetic substances, ferromagnetic, antiferromagnetic, and ferrimagnetic. So what is a diamagnetic material? These solids have paired up electronic spins and are weakly repelled by magnetic field. So the electron spins are in the same direction of this type. They have paired up electronic spins and are weakly repelled by the magnetic field. Example, sodium chloride and water. The second type we're going to discuss is the paramagnetic substances. The spins are randomly oriented and they have a permanent magnetic dipole due to few unpaired electrons and are weakly attracted by the magnetic field. The paramagnetic spins can be shown in this type. So you can see that there are few unpaired electronic spins. Example is copper oxide. Then we have ferromagnetic substances. In the substances, there is spontaneous alignment of magnetic moment in same direction. Example, iron and cobalt. So the ferromagnetic spins can be shown in this way too. The spins are aligned parallel in magnetic domain. Example, iron and cobalt. Antiferromagnetic substances. In these substances, magnetic moments are aligned in compensatory way, so they cancel out each other and net magnetic moment becomes zero. The antiferromagnetic spins can be shown in this way. You see that they are aligned in a compensatory way, so they cancel out each other, and hence the net magnetic moment turns out to be zero. The next is ferromagnetic substances. When magnetic moments are aligned in parallel and antiparallel directions in unequal numbers, it results in some magnetic moment. These are ferromagnetic substances. And here the spins are aligned antiparallel, but they do not cancel out each other. It's of this kind. They do not cancel out each other. So today we have learned about the properties of solids, the electrical and the magnetic properties. Thank you so much for watching my video. Stay tuned for more updates.